Hello there. Today we'll be doing minimal window substring. This particular problem, we will start off with the less optimized method and we will go to the more optimized method. Okay, so let's talk about this problem. In this particular problem, we are given a string and we're trying to find a substring that is of minimal window size. So in this case, after going through this entire string, we can find A, B, and C in this portion here, B, A, and C. And that is the smallest window we can have to have A, B, and C. So similar to a previous problem, you can use default dictionary to check the number of items of A, B, and C, and we can check that against and fill in those items for our window, and check that for those items if that is in our window. So let's do a shorter problem than this very long problem here, and let's count. Make sure. We're going to count A, B, and C. So let's just do that. If we have our window here, L and R, we can start adding items into our dictionary. So we have 1A, and we can have a D at 1, and then we can have a B at 1. As you can see, our matching dictionary is going to be A, B, and C, and it has no D, so we're just only going to check the items that are in the dictionary. So let's keep moving. We have an A for 2, and N for 1, and C for 1. Once we hit that C, we can now increment the L because we start closing our window because we have all the items that we need. So once we start closing the window, we lose an A, we lose the D, we lose the B, and once we lose the B, that means we are done iterating because we no longer have a window at which we have the substring, and that means it's time to increment the R, and now we have nothing. So in at that time when we have everything, every time we have everything, we're going to see if we can update our substring. Alright, so that's basically what we're gonna do, and so let's program it out. So first things first, if length of string is less than the length of t, that means it's impossible, so return empty string. So let's set our result is equal to empty string, or or none. We can set it to an empty string or none. I think we'll set it to none and we'll optimize later. So first things first, we're gonna have to find out what we're trying to match against. So match is equal to currently it's a default dictionary of int, and to find the matches for char in t, match t plus equals 1. Now we have our matching dictionary, what we need to match. So we're going to check. So same thing, default dictionary, and to generate this, we're going to go through a left and right pointer because we know that we're going to move right forward of every single time, so we can just do that. That way it eliminates a lot of code and makes it a little bit more clear. So we also need to set our left is equal to 0. So once that happens, let's see, let's add the character. So add char equals s of r. So check at add char plus equals 1. Oh, we had a fire alarm there. Let's keep moving on. So if we have a match, between match and check, then, while this is the case, we can move L plus equals 1. Every time we do L plus equals 1, we know what that means. We know that means we have to remove char. equals s of l, and check remove char minus equals 1. Also, this also means that if not result, we can set the result to our s of l to r plus 1, and else if well, right minus left plus 1 is less than the length of result, then we can also set it to result. So with that, we have moved the right pointer, we have moved the left pointer, and that means that we are done here and we can return the results. One thing to note is that we have not done the isMatching function, so let's get that done. And what we'll be taking in is two dictionaries, match and check, and we'll be returning a bool. So for key and value in match dot items, if key in check and value of the matching item is greater than or equal to, check of the key is greater than or equal to the value, then we can return true, right? Continue. Otherwise, we return false. A simple way to change this is the if not. If it's not the case, return false. Then we can return true afterwards. So all done here, and let's run the code. For our in range length fs. Let's see, returning null. All right, if result else empty string. Also, this is not supposed to be a problem. I don't know exactly why it's a problem right now. Let's check. So it looks like we never matched. Well, match and check should be the same. Hold on, that's weird. What is double A2? Okay, that's better. I was like, huh, that's really odd. Okay, here we go. Let's submit. All right, so we have a pretty clean solution here. As you can see, we have done exactly as we have said with the example. But a way to make this a lot faster is to check what we have and need at this particular point at each cycle. So we don't have to check every single key. The way to do that is set a have equals 0, and a need is equal to well, the length of t. We know, well, the length of set t, because we're gonna have that many characters that we need to have. And how we're gonna check if we have something and need something is that if char add char is in our check, and our check at add char is equal to match at add char, then we can say have is plus equals 1. This also means that we need to remove that char once we do a removal. So here we go. If check remove char is less than match add remove char, then have minus equals 1. Now this way we don't have to use is matching anymore, and we can say while have is equal to need. We can run the code again, and a similar result, and let's submit. Okay, as you can see, the result is much faster. Let's say about 5x faster. The reason being is that we no longer have to check each particular key, even though that is only 26 keys and it's still of 1. This is supposedly 26 times faster because, well, we only need to do our checking once every single time rather than checking every single key that's possible. So another way we can make this even faster is to filter out our string for just the index and the key and the character. That way we can skip many of these left and right, and we can just move our left from one index to the next important index. Of course, this will take a little bit more and a finesse in terms of coding, and it might take a little bit more time. But if we have time in the interview, I mean, this is something to show that you have you can keep modifying your code and updating. So let's do this as our last step, and we're going to finish off the video now. If you're done enough and you learned enough, and then you can start closing that video, and I'll see you in the next one. But for those who want to continue, let's continue. Okay, here we go. So in this particular problem, what we're gonna do now is create a filtered S. So this is going to be, whoops, a little bit tricky. All right. Filtered S. Let's set this to be an empty array. And so for I and C char in S, enumerate S. So this is going to be an enumerated S, and we're going to store filtered S is dot append the I and the char if the char is in a match. So that's the only time we need it. So this means that we're going to only do filtered S. And this also means that we need to generate our left index and right index. So left index is equal to, well, let's see, our left pointer. So filtered S of L, and our right index is equal to a filtered S of R. So add character, instead of R, we need to get the right index. And now we can add the character. Okay, left and right. Oh, that's not gonna work. We need our left and right index because we are updating those. And now we have to take that and copy this down here. Right minus left. No, that's wrong. We need our right index minus left index because left is only a pointer to a pointer. So that's what I mean. It's a little bit odd. So S of L, well, that basically means left index. And we're going to remove that. Character, everything looks good. Let's run the code. Let's see. Filtered S of R. Oh, right. So the first item is the index. The second item is the character. Okay, it looks like we have a issue here. Let's see. What happened was that why is this even a check? Okay, so we have an issue here. So we're gonna have to do some debugging. This is the hard part. So the hard part is to figure out which is which and what's going on, right? So as the right index should get the right item. And I don't think we need the char. I don't know exactly what's wrong here. Okay. So, I mean, let's start printing out stuff. That's the best solution I have. I think Did we redefine the left index here? No, that's the problem. So basically, what needs to happen is that this needs to be redefined here. And the right index, this right here, is not important. What we need to do is do the filtered S of the right of the first item. That's the add character. This way, we can update our left pointer. And let's update this into our test case. Looks good. And let's run this. Okay, so it's slightly slower even with the filtered characters. Let's check this one more time just to make sure that this is supposedly faster because we're removing items that we don't need. But in this case, it looks like it's actually slower. Even though we have filtered out the S. Yeah, that took a little bit of our time, but we got to it. This is the most efficient solution, and yeah, I think your interviewer would be super impressed with the optimizations that has occurred in this particular problem. It has gone very complex as we have moved into more and more items, and there's more and more concepts here that we are generating. So I think actually, because there's abstraction within abstraction, filtered S and everything. I mean, when another person comes and reads this code, like they're gonna be like, "What the hell? What is this filtered S? Why do we have a filtered S? Filtered string? Like, what's going on here?" Well, one thing to do is store valuable, important index of character. Okay, so we have filtered S here. Somebody knows what this is for checking. So this way, optimization, I mean, that way people know why we have the filtered S here. But make sure people know that we have a sliding window, even though the R does say that. And this have and need, let's move this here. A check and match, and the result. And we have the have and need there. So this way we know for sure what we're looking at. So we also want to move this down here. Make sure everyone knows what we're looking at. And yeah, we cleaned up the code a little bit to make sure that next time when we read this code, it is readable and we know what we're doing. Although it is a bit complex for someone to come in and read it for the first time, I think that it is for better code, and it speeds up our operations as time progresses, because we want to be able to slide our window faster than just through indexes that doesn't matter to us. So let's think about the O of n time, and let's close this video down. Okay, so what we're doing is we're going through the entire string once, And every time we go through the string, this is one time through enumeration. The second time is just through the R, and everything else is a one lookup time. So it's O of the length of string S, plus the length of T, because we're gonna go through that once as well. So that's all for this particular problem. Yeah, if you enjoyed this video, like and subscribe. If you want more videos, check the link in the description below. Thank you very much, and have a good one.